All right. Good morning, everyone. Good morning from the Bay Area. Good afternoon, good evening, wherever you're joining us from. Welcome to the next installment of tinyML Talks. This is the first local tinyML Talks organized by the Bay Area Group. My name is Ravi Sivalingam. I'm one of the organizers of the Global tinyML Talks. Today, we have a tutorial on microkernel-based hardware acceleration by Manu Rastogi. Just a reminder for everyone, please ask your questions in the Q&A window. Do not ask it in the chat. I will be monitoring the Q&A window and will be asking Manu questions as he goes through the tutorial. And another reminder, the slides and the video will be up on the forums in the next day or so. So yeah, as I mentioned, this is the first tinyML talk organized by the Bay Area Silicon Valley tinyML meetup. We've had in-person meetups before the pandemic started. We've had the global tinyML talks, and this is the organizing committee consisting of Manu, Ame, Mahmood, and Yupu. If you're interested in volunteering or joining the meetup, if you're joining the meetup, do scan the QR code over there on the left, and you can join on meetup.com. If you're interested in joining the organizing committee and volunteering to help organize these events, please email meetups@tinyml.org. I'd like to thank our sponsors for the tinyML talks, DeepLight, Kixo, Edge Impulse, Reality AI, Maxim Integrated, and SynSense. Thank you for sponsoring our global tinyML talks as well as our local talks. Additional sponsorships are available. Please contact Betty at tinyml.org for more info. Reminder about the next tinyML talks that are upcoming. On Tuesday, August 18th, we have Mark Stubbs from Shoreline IoT and Urmish Thakur from ARM-ML Research. This is going to happen on Tuesday, 8 a.m. Pacific time. If you're interested in presenting in an upcoming tinyML talk, either in the global talks or in the local talks, please do reach out at talks@tinyml.org. All right, today's speaker is Manu Rastogi. Manu received his BTech from India and his master's and PhD from University of Florida. Since graduation, he's worked with Qualcomm Research and HP Labs. And with Qualcomm Research, he worked on the Qualcomm Zeroth processor and later on the Qualcomm deep learning engine. He's developed signal processing algorithms, model development, deep learning model optimizations while at Qualcomm. At HP, he led the efforts around the machine learning at the edge and self-supervised machine learning methods for speaker identification. All right, take it away, Manu. And just a reminder again for the attendees, please do ask your questions in the Q&A. Because this is a tutorial, we'll be stopping several times in the middle to ask questions. So feel free to enter your questions at any time. Thank you. Go ahead, Manu.
All right. Well, thank you so much, Ravi, for that introduction. And thank you for the opportunity to present. As Ravi mentioned, this is a tutorial, so we will try and make it more interactive. So please do ask questions in the Q&A, as Ravi mentioned. So the tutorial I want to talk about is microkernels for hardware accelerations. And I will take it in. So the outline of the talk is essentially, I'm going to go through the motivation. We'll talk about matrix multiply on a simple processor. We'll talk about loop transformations, CNN on a simple processor, ML-based approaches to compilers, and discussion. At any time, these are the topics I will cover in detail. So if you don't understand some of the terminologies, I will cover all of them. Okay, so what is the motivation? The first and foremost is I've had a few people reach out before the talk also. What exactly is a microkernel? And if you're coming from the deep learning domain or the machine learning domain, it's not to be confused with the kernel trick in support vector machines. Microkernel with regards to edge hardware essentially means the assembly code which runs on the processor. So this is a diagram. It's a very high level view of a compilation process from tutorial's point. And what we're going to be talking today predominantly is going to be the machine dependent code optimization. So all these steps, if you're interested, phenomenal to learn about, but in this talk, we'll talk about machine dependent code optimizations. And that's what I mean by microkernel. So it's the code, assembly code, which actually runs onto the processor. Now, a good question to ask is, if you're coming from a deep learning domain or from the tinyML domain, why should you care about microkernels, right? I mean, normally you hit the compile button and it puts the code onto the processor. So one aspect is that microcode or an assembly code is actually responsible for orchestrating both the data as well as the computation. So it is important to understand how things are happening under the hood. And with deep learning, what has happened is, in recent times, there's been so much development and innovation, both in network architectures as well as innovation for hardware architecture which has come about. And a lot of times we would notice that even bigger companies have manual tuning which happens for optimization for both for performance as well as power. As it turns out, this is not just specific to deep learning. A lot of high performance and performance critical code will often be tuned, tweaked. So one classic example is signal processing or digital signal processing code. You'll find them, people tweaking and optimizing the code. Or at times, it's actually written entirely in microcode, right? So you'll go actually from a high level language onto assembly code for very critical pieces. So as I said, a good understanding of microcode basics. The purpose of this tutorial is to introduce you to some of the basics. It's not to turn anyone into a microkernel. I'm not taking away your compilers, but the idea is that if you understand what is happening under the hood, hopefully it helps from a tinyML perspective choose the right hardware, or at least ask the right set of questions, and maybe even develop better and more efficient algorithms. Okay, so with that motivation, I will jump right in. So what we're going to do is we're going to start with a simple processor, and I'm going to define a processor which, as I show on the right side. So there is a main memory, and a processor has 3 internal memories. So there's a temporary memory, there's an internal memory A, and there's an internal memory B. And this processor, a very, very simple processor, actually has a multiply and accumulate block. So you can think of arithmetic block. Multiply and accumulate is basically something which will multiply 2 numbers and add them to whatever exists, right? If you don't understand multiply and accumulate, you don't have to worry about it. Just think of it like a multiplier, okay? So a really, really simple processor. So 3 on-chip memories, a main memory, and a MAC unit, or an ALU unit. Before we go any further, let's define a few cost functions. Now, when I say cost functions, I don't want to differentiate between energy. So you can assume this to be whatever you want for simplicity's sake, right? This can be energy, this can be power, can be delay, or can be the energy delay product, or EDP square, whatever works, right? So we'll see how these costs, and when we choose to deploy a model or a network, how these costs come into play. So the 3 costs, again, to keep things very simple, that I'm defining is C memory. C memory is the cost of moving one number of 16 bits. Okay, so if 16 bits scares you, just one number from the main memory onto the processor. C mac is the cost of doing the multiply and add, or any kind of an arithmetic operation on the processor. CINT is the cost of moving the data between the internal memories onto the ALU. Okay, so really, really simple aspect. Okay, now I hope, are there any questions so far?
None yet. Please go ahead.
Awesome. Okay. All right, so we're going to look at matrix multiply. If you haven't looked at matrix multiply, so what we're going to do is we're going to multiply one matrix with another vector matrix. So let's assume the matrix size for A matrix to be 32 cross 32. So it's got 32 cross 32, 32 rows and 32 columns, and a B matrix which is of size 32 cross 1. Okay, so the total number of max multiply and accumulates are going to be 32 cross 32, which is the total sum. So typically, what are the steps? And this is just as a refresher, because the first time I looked at it after a long time, I had to remember how matrix multiplication is done. All right, so again, so we're going to assume, make an assumption here that the internal memory size, or memory A, is of size 32 cross 1, Memory B is of size 32 cross 1, and the temporary memory is also 32 cross 1. The main memory, you can assume it to be as certain terabytes, so we don't have to be worried about that. Now, the steps for matrix multiplication again are you essentially take this row A0, you multiply each of the elements with the corresponding elements of matrix B, which since this is basically a vector. What you're going to do is you're going to do an element by element multiplication, sum all the values, store the result in the temporary memory, repeat the same step for all the other rows, so A1 to A31, and store the results back into the memory. Okay, just standard matrix multiplication, nothing fancy. All right, now let's start looking at what would be some of the costs associated, and this is a slightly bit more complicated of a slide, and I apologize for that. But so the cost of transferring one row, so one row of matrices. So the first thing to realize is I cannot store, since the matrix sizes are very small, sorry, the memory sizes are only 32 cross 1, I cannot store this entire matrix into the memory. So I have to basically stream the data from the main memory onto my processor. Now matrix B is of size 32 cross 1, so that can reside entirely into the memory, which means I can do one transfer and I'm good to go. But for matrix A, what I'll have to do is I'll have to stream one row at a time. So the cost of transferring one row of matrix A onto the processor is going to be 32. The 32 comes from 32 numbers, so 32 columns in one row, plus one-time transfer of matrix B, which is again going to be 32 into CMEM. CMEM is the cost of transferring the data from the main memory onto the processor. Now, what is the compute cost for a single row? Now, we assume that all arithmetic functions are of the same cost, CMAC. So the cost of computing a single row is going to be 32 multiplied by CMAC. So CMAC is the unit cost of multiplying two numbers, adding two numbers, and there are 32 numbers that are getting multiplied. So once we compute this result, we need to store this data back into the temporary memory, okay? So the total cost, so temporary memory cost is going to be 1 times CINT, because that's the one unit that I'm using. So what will be the total cost? Now, one good point to think about here is, since I don't have any interdependencies between the rows, I don't really need to save the data back into the memory, the temporary memory, right? I can just save it back into the main memory. So the transfer cost, the reason I put this result in is because somewhere in the succeeding slides, we will see that temporary memory starts playing a bigger role. So the total cost is going to be 32 rows of A, which we're going to transfer, multiplied by 32 numbers per row, plus 32 rows of B, plus one number per row, right? Compute cost is 32 rows of A multiplied by 32 MAC aspects that we're doing in the row. And temporary storage is going to be 32 numbers to store if you want to store the results temporarily in the memory. And if you write back the results, it's going to be 32 numbers that you're writing back. If you do add all these numbers up, the total cost is going to come out to be this, okay? So this is this cost. And if you notice in this expression, I've actually ignored the temporary storage, and I should have probably deleted it here, but anyways. So the first term that I'm getting because I'm streaming the two matrices in. The second term is the compute cost on the processor, and the third term is the cost of writing the data back into the memory. Okay, does this make sense to everyone? I mean, if there are any questions, I'd be happy to answer.
Yeah, this is good. Kind of clarify the individual details. The question about the CMAC, right? So that's a cost for a multiply plus an add operation.
Right. So yeah, go ahead.
So when you actually do a 32 element-wise multiplications and then adding them together, technically you're only doing 31 adds. Or is it explicitly done that way? I don't know if the add itself saves a lot compared to the multiplications that you're doing.
Not really. So in reality, the cost is going to be very fractional between a multiply and accumulate and an add. What typically happens in a micro instruction set architecture is, you'll have an ARM architecture, for example. The add unit, depending upon what the architecture, it's quite possible that an add rides on top of a MAC unit. So essentially, when you do an add operation, underneath it might be doing a MAC with a multiplication of 1 and initializing the accumulator to be 0. So again, it depends upon the micro architecture, the way it has been defined. But you have a fair point that it will actually be only 31 additions. I just wanted to keep it simple. That's why I've kept the cost of any arithmetic computation as CMAC.
Okay. Yeah. Thank you.
Does that answer your question? Right.
Yep.
Okay. So we were here. So this is the cost. Now, let's say some designer came in and there were some hardware constraints and they decided to slash the memory sizes from 32 cross 1 to all of them being 16 cross 1, right? So now we have a bigger problem. Earlier, we could stream an entire row into the processor at one time. Now what happens? So what happens now is, remember the matrix size is 32 cross 32, which means logical choice. And if you are experienced with kernel development, you might be inclined to say that why am I streaming them row wise? I could also done it column wise, and we'll cover that case too. So one way of doing this is at one point in time, I can stream 16 numbers. So that's why I've broken up one matrix row into two subsets, right? A00, which is the first piece, and A01, and that's the same nomenclature. What I can do is I can stream in data this way, right? So I can stream in A00 this time. So if you're doing this by hand, what you would do naturally is you'll multiply these 16 numbers with these 16 numbers, then these 16 numbers with these 16 numbers, and you'll somehow figure out how to store the partial product. So the streaming data, the streaming sequence actually looks like this. First, you're going to stream A00, then B0, do the computation of A00, B0, store the results out, okay? Then you will come back and you'll stream A01, B1, you'll get this second tile in, multiply them, store them. Then you'll go to the next row and you'll save, you'll do the same operation. And this will happen for 32 rows. So what happens to the computation cost? So the computation cost is increased, right? I mean, we are effectively streaming the B matrix 32 times. Why are we doing this 32 times? Because you'll have 32 tiles here and then you'll have 32 tiles here. So we're essentially doing, so as you can imagine, the cost is going to be high. Now, what about compute, right? Compute cost will remain the same. And why does the compute cost remain the same? I mean, clearly we've broken on the computation. And one way of thinking about this is, if you have to multiply 100 numbers, you have to multiply 100 numbers. There's no getting around it, right? So the total amount of computation in terms of the multiply and accumulate still remains the same, okay? But what about the partial products? So the partial products, as Ravi had very wisely pointed out, what you can do is you can leave them in the MAC unit. So you remember I said a MAC unit is a multiply and accumulate. So you multiply two numbers and you add to whatever exists in the accumulator. So what will happen in this case is when I stream the data, I can just leave this product in my accumulator, stream these two numbers, and these will just get added to it. Does that make sense? Okay. So what does the cost look like? So the total cost looks like this. So this is again my computation, okay? And I have 32 numbers which are going back into the memory. But if you notice, comparing this to the previous cost that we had, this is a much bigger expression, right? Compared to this. There's a term of 3 which comes in the head of it. And the reason that comes is because we're streaming the B matrix at least an entire time, okay? So 32 times the B matrix gets streamed into the main processor. In the previous case, we just transferred the whole B matrix in one go and we were done, okay? Are there any questions on what is happening here or anything I can clarify?
Yeah, so I had a question about B0 being, I don't know if that's what you mentioned about column wise, is that can we store read in B0 once and just do the light pink, like the A00, A10, A20 partial products? Of course, then we'd have to store 32 partial products and move them in and out of the MAC into the maybe temporary memory or something.
Right. So that's a very good point. And let me, so what happens, so Ravi's question is what happens if I decided to do this column wise, right? What will happen is if you do this column wise, you will have to save 16 numbers, right? So the column wise splitting will be 16 numbers going this way, right? And 16 numbers going this way. And then since you can only store 16 numbers in the temporary memory, what will happen is at some point in time, the cost of moving the partial data back and forth will become prohibitive. So that's why if you notice what I've done is I've left the CMEM and the CMAC and I haven't really defined what those values are. But I can tell you, and as most people in this forum know, the cost, and when we say both in terms of energy as well as delay, of moving anything back and forth from an external memory is extremely high. So generally, if you do the partials that way, it becomes, actually there is a case, and that I will leave for the interested audience to look at, where actually it makes sense to do that. But we'll talk about it in a bit, okay? So any other questions on this, how I got the cost and why this is a very naive and doesn't make sense?
Oh, this looks good. Thank you.
Okay, awesome. All right, so another smarter way of doing this, as you might have guessed, is to stream the B0 matrix in one go. And instead of doing this zigzag fashion of computation, what we do is we do A00. We stream B0 once, B1 once, we keep them around in the local memory, and we do the multiplication and we store them. Okay, so we are now going column wise. And I think this is what Ravi you were getting at, right? So what is the computation cost? So if you think about the movement of the A matrix and the B matrix, that still remains the same because we stream them once and we are done. Okay. What about compute? So you might be tempted to think that the compute cost remains the same, but it may not be the same. And the reason it may not be the same is because now, as Ravi was asking, you have to save these 16 partials somewhere, right? I cannot save. So once I go through this entire thing, I have 32 partial results that are available. I only have space for saving 16 at a go, which means I have 4 sets of partials that are going to come out of this. So somewhere I need to save them. I can only save 16 at a time. So that cost is going to go up. And the reason I say this is instruction set architecture dependent is because it really depends upon whether your ISA or your micro instructions allow you to initialize. So for example, if I save the first 16 around in the temporary memory, and then I come here and I compute the next 16, right? These 16 have no use. I mean, I'll have to one way or the other move 3 16-bit chunks out in the memory. But there's another challenge. The challenge is when you stream those 16 numbers coming in, whether or not your ISA allows for you to initialize your multiplier or your MAC unit using that. So that becomes a challenge in itself. So there is a hidden cost of moving partials back to memory and stuff. There is a second order effect, which, and you know, just for a minute, if we ignore what I said about the cost, that can be anything. What you will actually save is the energy from the movement of data, right? You will not really save anything in terms of time. And why is that? So the reason you don't save anything in terms of time is because the processor is anyways going to be idle. So if you have B0 available, the processor still has to wait for A10 to come in, right? So in terms of time, in terms of throughput, the throughput of this guy, if you ignore for a minute the partial part, which is going to be very minimalistic if the matrix is large, the throughput is going to remain the same, more or less. But you do save something from the energy aspect by doing the tiling in this way. Does that part make sense?
Yeah, it does. So I had a question, and I know you've thrown kind of abstract names and not the actual numbers on the CMEM, CINT, and the CMAC. We're noticing, and this may be from some of the larger compute devices, not really in the tinyML side, that they've gotten to the point where they can do a lot of max really well. And memory movement, because of the kind of arithmetic intensity of operations in CNNs, they realize that they're spending more time, they can't feed their max fast enough. So this sort of thing about, you know, the processor being idle and waiting for the next 2 inputs or how many ever inputs it's putting together, that seems to be an issue, and people are trying very innovative ideas about spreading memory all throughout the processor so that even the time to move that to the Mac unit is reduced. So can you comment something about that?
Sure,
And
absolutely. So one of the things which we realize, and I'm glad you brought it up. So I'm going to talk about, very briefly talk about compute and memory. So I think that will talk about the, so far, there is nothing which says this matrix multiplication is for an inference or for an edge device, right? As you rightly said, if you're training your own models and if you ever fire a command known as NVIDIA-SMI, you tend to see that if your GPU units are starved for data, and if you're using a PyTorch data loader, you would notice that there is something called as number of workers. So for example, I have a very close friend who decided to invest in a very good multi-GPU system. However, he cheaped out on the processor, and the processor is the one which controls the data going in, right? So what you're talking about actually is, in terms of hardware architecture, there are two bottlenecks that we often encounter. One is compute bound and the other is memory bound, right? So what this means is, essentially, compute bound means you have data available, you have so many Mac units in, you cannot keep up, right? So fully connected layer, and again, I get into trouble in front of who I'm saying, but generally fully connected layer are going to be memory bound, whereas your convolution layers are generally not, are more compute bound, right? So there is a distinction, and there is another aspect of this which I didn't talk about, and since you brought it up, is this also means that you need to do some kind of a smarter pipelining, right? So those of you familiar with pipelining and FIFOs, what you will really need to do is, while you're doing this computation, you actually want to go ahead and fetch B0 tile to come in, right? So then that means you have the, so what you actually have with the memory is data which can be pushed out simultaneously as this new data is coming in, right? And there are certain architectures in academia which talk about things like this. Okay. So this approach, if you're coming from a compiler's background, is known as memory tiling. It's a very standard term. So if you Google memory tiling, CNNs, there's a whole bunch of academic research which is around that. Can I move on to the next slide?
yeah, please go ahead. Thank you.
All right. So we were talking about this, and I have done this analysis a few times, and what happens is, so I wanted to compare the three schemes. So the first one is, which we looked at, which is, you have enough memory, you can stream in, you can go with a row. The second one is the unoptimized version, where we were streaming the second one 2 times. And the third one, and actually this should not have been 3, this should have been 1, but anyways, I'll correct this in the final slide deck. So the interesting thing I wanted to note was, assuming, so this term and this term are going to be essentially the same because you have the same amount of memory movement. There are these 2 extra terms that are getting added at the end for the optimized case. And the reason these are coming is because now we have to move the partials as well as 32 CMAC, because I have to add partials 32 times. I mean, 32 numbers have to get added, right? 16 numbers from one go. So that's why you get this term. Now, what is interesting is, and in this as an exercise, I'll leave if people are interested. This is a very simple process, it's a very simple use case. If you go on adding more and more constraints, so if you reduce the memory size further 4x1, and depending upon what values of CMM you choose, it turns out the best or the most optimum memory tiling scheme that will happen will be something which looks like this. So it will be a combination of actually a row. So instead of picking up either a row like this or a column like this, you're actually going to be picking up blocks of 4x4 or 2x2. And that, as it turns out, is the most optimum one, depending upon, again, what are your costs, because the amount of data which has to move and the partials which have to get computed, this starts becoming very, very dominant. Okay. And as I said, it's a very simple example. The other approach which also can be done is, you can think of this whole cost expression as a convex optimization problem, right? So you can say that if I had these costs, I can actually draw a polynomial out, and I can actually cross the convex surface if it turns out to be convex, and you can find the optimum point. But that's also an exercise which can be done. Typically, that is not done, at least in the industry when I've seen it, it's not done. The reason is this is a very simple processor. It's good for understanding. A realistic processor will have so many other overheads and so many tiny details. Plus, this is a matrix multiplication, right? As I'll show in the in some of the succeeding slides, that for a convolutional neural network, things become much more complicated. Okay. Any questions so far on the matrix multiplication part? And how am I doing on time?
Yeah, you're good on time. You mentioned that this could be treated as an optimization problem in itself. And anyway, that's an optimization problem. Machine learning is fundamentally an optimization problem. So have you seen effectively like compilers that try to optimize each particular input problem set differently?
Right. So I have so if you hold that question, I have a slide on that and I'll talk about it. Okay?
Excellent. Yeah, please proceed.
Okay. All right. So one thing which I wanted to say, and I'm going to take a little bit of a digression into compilers aspect. I'm not a compiler. I'm not formally trained as a compiler person. I did study them for a little while in one of my jobs, but one way, so all this stuff we talked about, as it turns out, the guys who do actual compiler stuff, they've been doing it for ages. And memory tiling can actually be looked at as a loop transformation. So what I've done essentially is, this was my matrix multiplication, right? So it's a very straightforward, not really a matrix multiplication, but multiplying with a vector. And when you tile it, this is how my loop starts looking. And when the slides come in, you can check that it's correct. One key thing which I want you to two key points I want people to take away from this particular slide is, one, the aspects of memory tiling can also mathematically be looked at loop transformation. And the reason I say loop mathematically is because there is enough amount of theory, mathematical theory, which exists in how do you transform one loop under certain constraint into something else. If you're interested, there is something called as polyhedral optimization, which is what Poly, LLVM, a lot of these tools use. And I can talk more about that later. That's one takeaway. The second takeaway for this talk, more relevant, is the more you tile, look at this, right? I mean, we intuitively, it made sense, but look at the number of for loops that I've added, right? And these intermediate calculations. And one thing which I haven't added is, if you think about it a little bit, depending upon which tile you are in, you might have to initialize the C matrix to 0 versus taking the prefix, right? So there is going to be an if-else statement. What this means for a reason, as a simple example, memory tiling becomes very tricky. It's a very complicated control logic. Okay. Memory access will become trickier. So if you remember, if you go back to your, C++, at least the interview questions, right? If you're storing matrix as a row major versus a column major, that no longer applies, because now this matrix, when I'm going to pull it out in this way, I have to pull these numbers like this, then I'm going to come back here, I'm going to put this. So the memory access pattern becomes very complicated, right? And this is again for a simple example. As you reduce your tile sizes, the memory, how you save it becomes more complicated, right? Now you may be saying that I want to stream the numbers only once. It doesn't matter. And I'll show one example in case of a convolutional network. The memory access pattern is just through the roof. Okay. The other aspects, the other practical aspects of this is, the more complicated your memory controller is, it will have delay. The second is, it will need dedicated, it will have a silicon area cost to it. That will also add energy. That will also add to the bottom line cost. So the more complicated of an optimization you do in terms of saving energy or throughput, you do pay for a cost in the silicon domain, right? Okay, any questions on this?
Yes, so you mentioned about the row major and column major, and that brings up an interesting point. So typically, unless you're a MATLAB person, most of the time data matrices are actually stored in row major order. So accessing the next column element on the same row is cheaper than accessing something in the next row. And also when it comes to in real systems, things are really word aligned. So if you're accessing bytes, then accessing bytes within the same word, or like accessing 4 bytes at a time, is easier than accessing like at not word edges. And the other extreme case is in CNNs, when you're actually doing one by one convolutions, or like the second part of the depth separable part, where you're accessing just one, let me call it one row column, but along all the channels, that becomes, you're jumping quite far ahead. So how does that how do you optimize something like that? Is
Correct.
there a
So
better way
there
to
are,
write it out in a different way so that you can access
yeah.
it better in terms
So yeah. So I will talk. So that's a very good question, and let me just give me, once I get to the convolution part, I'll answer that.
Sure.
Okay.
Okay. Sounds good. I think I'm jumping the gun here.
No, no, you're fine. I mean, all right. Are there any other questions from anyone else?
No. Yeah.
Okay, awesome. All right, so a few more transformations just for the sake of completion this was the simple multiplication so this is another simple multiplication we're doing. What we're doing is, all we're doing is multiplying a vector. This is not matrix multiplication. We have an A vector and B vector, and we're just doing an element-wise multiplication. A lot of times, if you're dealing with microkernels, or if you're dealing with compilers, or even computer architecture, you'll hear this term of a vector multiplier or a SIMD. And again, I've gotten into trouble for calling a SIMD a vector and one way or the other, but people can come and yell at me later. But so what a vector multiplier essentially is, that I will have, or a SIMD is single instruction and multiple data. What that means is, I may have one particular instruction or one particular command for my ALU, which will allow me to multiply, say, maybe 100 numbers in one go, right? So it's a single mathematical instruction, which is multiply, and it's saying is multiply 100 numbers in one go, right? So that's why it's called a SIMD or a vector multiplier. You're multiplying an entire vector in one go. The other aspect which comes very common is loop unrolling. So loop unrolling means, so think about the processor we were talking about. We said there's only one ALU available. Imagine you had 5 or 4 ALUs in this case available. What you could do is, you could multiply 4 numbers in parallel, right? So slightly different than SIMD, but essentially it's doing the same thing, but you have 4 different instructions available. In case of a SIMD, you essentially have one ALU which is taking in multiple aspects. Now in a multi-processor system, so you have 2 separate processors that are available, you can actually split the loop. So this is also known as loop splitting. Again, all these you can think of them in as doing this essentially the same thing, but the underlying implementations are different, and that will have consequences on what you're trying to do. So for example, we are looking at this normal element by element multiplication here. But if I was doing matrix multiplication, this would be a very different thing, particularly if I'm multiplying something like 32 cross 32 with another square matrix. Okay. All right, so I'm going to move on to the next one. So as I said, people talk about a lot of, as I said, people who do compilers have been doing this and studying this for a long time. So why is it that you can't pick up a loop unrolling and tiling? And this is also going back to what I was trying to motivate towards picking up the matrix size. So if you think about it, the memory tiling actually happens because you have a constraint on memory. Loop unrolling happens if you have too much compute available. Okay. Now, loop unrolling and tiling together make a very complicated. You just cannot say that I'm going to unroll the maximum number of times and I'm going to unroll, I'm going to tile the maximum amount I have available. It actually has a very strange kind of a relation. This is slightly an old paper from 2002, but it's a very good paper to look at because they talk about how these aspects interplay. And as you can see on this axis is the unroll, and on this axis is the tile. I forget what was the workload, but essentially, as you can see, as you vary them and as you increase them, the performance type does not. And actually, in this side, with the tile size is decreasing, it actually goes up. Now, so there is a lot of mathematical constructs, heuristics that are available in the compiler domain. Choosing transformation is not trivial. It's widely researched, studied, used by compiler community. Optimizations are actually typically stacked. And at some point I was reading the papers and it said the GCC can do multiple passes to figure out how do you stack the optimizations, right? So if you're doing unrolling by certain factor, whether or not it works out for something else. If anyone is interested, Wikipedia actually has a very good set of, I think there are like 15 or 20 different loop optimizations which are listed out. All right, so I'll move to the next one. So let's talk about a single.
Quick question before we move on about this previous slide. So given that this is I mean, not that we're running gradient descent on this, but essentially this is a non-convex surface. So if you are looking to trade off one versus the other between two different instantiations of how we would do this, what is better, like the unrolling or
So I think I think that's a good point. So it again depends upon. Let me put it this way: let's take an extreme case. Say going back to the GPU example you were talking about, right? If you have infinite amount of compute power available, right? You would want to unroll as much as you can. So imagine in case of our matrix multiplication, if I had 32 multipliers available, I would do 32 separate multiplications. But on the other hand, I need to be worried about how I'm going to combine them, right? And then that's where it becomes the data movement problem. Can I actually move 32 chunks of data in my data bus, right? So then if you have higher compute as compared to higher data bus, something or the other is going to be a mismatch. So the two have to be actually matched and moved in tandem. Like for example, in this case, right, as the tile sizes decrease, right, for a loop unroll factor or something, it remains constant. But the moment you do a loop unroll, the processing time actually goes up, which is sort of counterintuitive, right? You processing more and more, but you're processing. I mean, you're processing more and more at a given time, but your overall time is going up. So it is not, unfortunately, it is not trivial. And as I said, there are about 15 to 20, at least that I'm aware of, 15 to 20 other optimizations which exist, right? So this is only an unroll and a tile size. Now you can imagine a 15 to 20, and I'm sure those are the other ones which exist. The loop optimizations become very, very tricky. In fact, there are a whole bunch of machine learning papers on compilers which actually talk about doing space optimization for what sequence. So out of say 200 optimizations, which ones to pick up and what path to take. So there is all this stuff which is already in the literature.
Okay, thank you.
Okay, all right. So I'm going to move to the next one. So let's talk about a CNN. So what I did was so I have an input which is of size 5x5, and to keep things really, really simple, I want to just assume this is a single image, no channels, one channel, and a single lonely kernel. So if you think about it, what is going to happen, and the stride is equal to 1. So the first time the kernel remains the same. So the first time you'll be computing this. So essentially the way you do it in a CNN is you multiply each of these element by elements, sum them, and you get the output, right? Next time you move the stride, so you move the input in this receptive field, you do that, and then so on and so forth. I haven't shown the third row essentially because of the real estate problem. But what would happen in the third row is essentially you look at this set, and then that's this set, and so on and so forth. And this would be the output coming in. I'm assuming everyone is super clear about this. Okay. Now let's go back to our processor and assume that the processor has following memory constraints. So we had 32 cross 32 because we are looking at a very small image. Let's say my A memory is of cross 3x3. My B in memory is 3x3. Since I have only one kernel, what this essentially implies is the entire kernel fits in one go, right? So the only challenge I have is moving A back and forth. C memory, I don't really use it, but I'm going to ignore it. But if you want to make life complicated, you can assume it's 1x1. It doesn't really change anything because one receptive field is generating only one output. Okay. Are there any questions on what I'm trying to do so far?
No, go ahead.
Okay, awesome. So I changed instead of the numbers, I changed this to the notation, which will be much easier. So A00, row 0, column 1, and so on and so forth. So if you look at only the top row, this is the computation that is happening. The one in the red is the computation that's happening. So in the first go, we are looking at doing a matrix, essentially an element-wise element multiplication and then adding the values. And the second one, we're doing it. So since we can only fit a matrix of size 3x3 inside the processor memory, one solution would be to just stream this in one go. In the next go, just stream this matrix and this matrix. As you already saw, this would be wasteful. Why? Because I already have these two columns available in my processor memory. So it doesn't make sense streaming another one. Again, this will save energy, not necessarily the time, right? You still want to save energy. So it makes sense only to load the new stuff, right? So what does the new stuff look like? So I changed the color notation. So basically any new data coming in to the processor is denoted by this yellowish blob, and the existing data is green. Okay, so in the first time when we're doing this, all this data has to be streamed in. The next time you move in, you are only moving in the green. I'm sorry, the green data already exists, so I'm going to only tile and move in this one. And third go, I'm going to move in this one, and this is what my output is going to look like. So I'm going to the first one. This guy will calculate the first output. The second one will calculate the second one, and the third one will calculate the third one. Now, so the good question to ask here is, what output should be calculated next? So from these 6 remaining boxes, which one do you think should be calculated next? Anyone wants to take a guess?
The output below the 1, because you've already got 6 of those.
Man, come on, you're supposed to be okay. Anyways, yes, you are absolutely so you're absolutely right. You're 100% right, Ravi. The reason for that is intuitively, you would think that, we did this, and because on pen and paper, we would go naturally to this. If you look at this tile versus that, which is the first one is going to calculate this first one, and the second one is going to calculate this one. If you look at the green versus the yellow, in this case, we are actually moving in 7 pieces of new data. In this case, we are only moving in 3. So again, going by the additive principle, it makes sense to calculate the thing. And Ravi, you're absolutely right. Okay. So then the data movement actually looks like this, and the output is actually going to get calculated like this in a zigzag fashion. Okay. Now, I'm going to go to the partial question a little bit. So this is how my data will look like. And again, I haven't shown the third one, but you can imagine that the third one will slide down and then you'll go back like this. So this is how the memory, so this is going back to the question that you were asking, Ravi. What about the memory row major and column major? So I actually sat down and I tracked what does the data movement look like, right? So you're accessing the data in the first go like this, then you go over here, you access this row, this column, then you go back and you access this column, then you come down and you access this column, and then you access this row. So if you look at it, it's a fairly complicated. When I was drawing it out, I got confused myself because I missed an arrow and I was like, what happened? So it is non, and this is a very simple CNN we are talking about, right? So this is the memory access pattern, right? In a realistic scenario, a memory access pattern for a 2-dimensional or a 3-dimensional, which is typically the case for an image, right? You have convolutions which are happening in 3 dimensions. It's a very, very complicated pattern, right? So the question I think you asked is, how do you deal with it, right? So one question is, there is, to the best of my knowledge, it is very difficult to draw a mathematical expression which will give you something like this. I may be totally wrong, maybe somebody's figured it out. One, depending upon what your constraints are in your main memory. So as I said, if the main memory is certain terabytes, one way of doing this is you just pad everything that you are accessing, and you can just access everything in a row major and a column major. So wherever you want to make a transition in the main memory, you just pad values in, right? So you can repeat this matrix, you can bloat it up. That's an easy solution to do. There are other tricks and other techniques which also exist in academia. I mean, you can do some other things. The easy solution is, if you have silicon cost available, you can actually go ahead and build a very, very complicated DMA engine, which can actually move around in whatever way you want. But again, that's going to come at both the design cost, silicon area, energy, and all those things. Now, the other thing which I did not talk about and very conveniently ignored is partial products, right? Imagine the same thing, in this case, if the matrix size was, if the memory size was 2 × 2, what will happen is, in order for me to calculate this patch, I'll have this access to just 4 elements. And then I'll have to move them this side, and I'll have to store the partials somewhere. And then the partials will have to be stored somewhere in the main memory. And then this access pattern gets more complicated, right? So the cost, what I'm trying to relay is, the cost of the DMA engine is something which I haven't accounted for in this. So becomes very, very, very complicated. And this, one of the reasons of this is, as you talked about, depth-wise separable convolutions. both in terms of compression and quantization, there is a lot of work being done. And the reason is if you can compress or quantize, you can move more data in one go, right? So for example, if your data bus is a 16-bit wide, you can move two 8-bit numbers. Or if they're 4-bit, if they're 4-bit numbers, you can move 4 of them in one go. And that gives you a lot more access, right? So if you're just pulling this row, you won't mind pulling the 4 other values because it just comes free of cost. So there are other things that can be done. The last point which I want to make is, unlike the matrix example, where we could calculate a very nice polynomial function and optimize it out, in this case, in a realistic system, it becomes very, very complicated to say theoretically this is the maximum you can get. In fact, I posed this question to somebody who worked in compilers, and he said that as codes become more and more complicated, it's very difficult to say how the actual theoretical best looks like, which also means that it's quite possible that you have some kind of some kind of a compression or a quantization technique which can help move things around. So very, very complicated to estimate this cost. Are there any other questions so far? Because I'm nearing the end anyways.
There are a couple of questions.
Sure.
And I'm not familiar with this, but so are systolic arrays better for this purpose?
So so there was a paper called as Dian. Now I forgot the full name. There are 3 or 4 papers which talk about systolic arrays. I think they won the ISCA Best Paper Award 2 years in a row or something like that. So they actually looked at systolic arrays, and you're right, systolic arrays are helpful, but then again, it also still depends upon how you're moving the data, because systolic arrays is essentially tiled computation. I'm not an expert at systolic arrays, but my understanding is that, so if somebody is looking at systolic arrays, I would definitely recommend looking at Dian now paper, and if you're not able to find the paper, reach out to me after the talk and I can send you the references.
Yeah, we can definitely post that on the forums as well when you find it. Yep.
Right.
One other question is, what about the difficulty in sparse matrix multiplication? Should it be more pronounced, or is it easier? Because typically sparse matrix multiplication, of course, involves fewer operations, but because things are may not be structured, it may not be structured sparsely.
So sparse matrices are interesting if you can take an advantage of it. So I'll talk about, so hold on to the sparse matrix question. I'm going to talk about it more when I talk about the binary networks.
Okay.
Sorry.
Thank you.
Okay. Any other question? No?
No.
Okay, I'll move ahead. All right. So since I have only 8 minutes left, I want to try and wrap it up. So as Ravi, you were talking about machine learning and compilers, right? So the 2 most rather well-known aspects, one is called as TVM, which is tensor vector machines, and the other one is called as Facebook Glow, which is from Facebook. What these do is they try and model, so these are the 2 graphs from the TVM paper. What TVM, so in the traditional auto tuning, what you do is you run on a machine and you'll do a black box tuner, it will be a manual tuning that you're trying to do. Auto TVM, actually what it does is it looks at both heterogeneous as well as homogeneous device clusters, and it can actually tune your optimization space. So for example, if you're just looking at tiling as well as unrolling, right? If you have a 100 cross 100 matrix available, the minimum number of, you can at least do it by 100,000. You can tile it 100,000 times, right? Each one of them, one element. And what auto TVM does is it actually tries and runs a bunch of experiments, and it tries to figure out what is the optimum. So it does, it builds a model of the computation space for different hardware. And on their, I haven't looked at TVM in a while, but on their website, if you're interested, you should definitely go check it out. They have gone ahead and started supporting both Intel CPU, ARM CPUs, NVIDIA. In fact, this is one result which is there. Again, this is from 2018. What they've done is they've simulated these different models, and if you look up at it, they have actually simulated. So I know that maybe I don't have this. They actually did this on the NVIDIA 1080 Ti GPU, And I believe the results, if you look at the results of TVM auto-tuning them, these are pretty impressive results. And they have far more results where, you can actually let it run for a while on the, you can actually let it run on the computation machine, and it'll automatically figure out how to tune and how to time and everything. And what is impressive, at least if my memory serves correct, is they beat, I think, NVIDIA's published numbers on, at least that's what I remember. The numbers were very, very good. The other similar approach is looking at Facebook Glow. I haven't looked at Facebook Glow in more detail, but it's essentially similar kind of an idea, except I think Facebook Glow works more in the computation domain. It tries to fuse computations, but you have to read up more about it. Now, with regards to ML techniques, I actually read this paper and I highly recommend if people are interested. This is a survey paper in 2018. And I was quite surprised. For a very long time, I thought TVM and Facebook Glow were the only deep learning or machine learning based techniques. As it turns out, the compiler community has been trying machine learning since 90s, right? So Bayesian networks and everything, both in terms of what optimizations to apply and also in the sequence. So if people are interested, this would be a good go-to paper. At least it's up to date till 2018. I didn't really talk about other compiler frameworks and the optimization. One of the optimization is polyhedral optimization. What it does is it converts a graph, and you can read up more. And these are some of the polypluto and pencil in particular are the ones which are based on polyhedral optimization. So what polyhedral optimization essentially does is, if you have a graph with certain dependencies in terms of data, so think of multi-layer LSTM, right? You have one layer which is going to depend upon the second one, certain outputs, and so on and so forth. If you do the polyhedral optimization, it does something magically that it redirects the graph so that the dependencies become coherent in time. So they're concurrent in time rather than sequential dependency. Very interesting. Mathematically, I found it to be dense, but if people are interested, they should look at that. Last but not the least, since so GEM kernel stands for generalized matrix multiplication. And I believe Pete Warden, who's also part of the tinyML, he actually has a blog which says why GEM is the future of, why GEM is at the core of deep learning. And this is a very good paper and actually talks about GEM kernels and different strategies. If you have certain processing requirements, if you have matrices which are of particular size, vector, matrix. So it's a very interesting paper if people are more interested in matrix optimization. This would be a good paper. Okay, and last slide. Haha, 3 minutes to spare. So, okay, so what are the key takeaways? One is memory affects the cost of data movement. Memory affects the cost of data movement more than it affects computation, right? So computation, if, as I said, if you're multiplying 100 numbers, unless and until you do something like SVD or something where you can reduce the number of MAC counts, you will have to multiply 100 numbers. But memory, depending upon how you multiply, is going to change the total time, energy, and everything. If you are, what I have typically found is if you're in the mid-memory range, if you're in a very low memory versus a very high, low memory, then computation can become prohibitive, as you saw, right? If you have very low memory, then the cost of even adding the partials will go up. But in case of mid-memory range and the cost of data movement is going to be the dominant factor. Quantization and compression are essential because more data can be moved between memory and processor in the same way. And I think somebody asked about, somebody had asked a question. I said I'm going to talk about it more when I talk about binary networks. So one of the caveat of sparse matrices, one of the caveats of quantization, compression, and even sparseness, if you have hardware which can take advantage, if you have hardware both in terms of the compute engine as well as in terms of data movement, then yes, sparseness as well as compression and quantization makes sense. So as an example, binary networks are very, very popular, right? And a lot of people look at it. Unless and until your data bus, and Ravi, I think you brought it up that, data typically is word aligned and it moves in terms of quantum of words, right? So it will move maybe 16 numbers, 32 numbers in one go, which will be your one word. The problem is, unless and until you can move and access data at a one number or one bit at a time, which typically does, I mean, at least I haven't seen it, one bit at a time, it'll be very difficult to take advantage of this. What you'll have to do is you'll have to pack your 16-bit number as a, each individual bit being representing one bit of them. Then also you're moving a large quantum, whether or not you're required to do it or not. So that's one problem, right? So the obvious solution is if you have an existing piece of hardware and you're trying to run a binary network, you just you'll store one number at a time, everything else in the word is going to be a zero. So you're still paying a cost in terms of data movement. And of course, you can come up with some strategies where you say, if it's zero, I'm not going to move it or something like that, but you're still paying cost, right? The other thing is in terms of computation, if you look at the binary networks, it actually requires a pop counter as well as an XOR, right, as a multiplier. Unless and until the hardware, if the hardware accelerator actually is just a big MAC array, you probably would not have a XOR-based multiplier. So which means a dedicated piece of hardware has to be built for that. Which means even though on principle, when I did the network on PyTorch or on TensorFlow, I get advantages from compressing the network and quantizing it, and maybe it works very well on NVIDIA GPU, but when you go to an accelerator for inference, it may not work. So again, this is a classic case where there's a disconnect between what the hardware is capable of doing and what you can do with binary network. Another, if I were to take it in extreme, if you are a CNN accelerator and you have very little control plane logic, you can't do a random forest or a decision tree, because a decision tree is essentially if-else statements. And it might be very lightweight on a CPU, but if you have only a MAC array available, you cannot do and of course, this is a very unfair advantage, but taking the extreme. The same thing goes for sparse matrices. Unless and until you have a very efficient way of storing them and then utilizing them in the hardware, chances are it'll be a disconnect, right? I haven't worked a lot on sparseness. I'm aware of some schemes, but so as I said, one of the things that has happened with binary networks is a lot of, since binary networks are tiny networks, people have started building these compute and memory accelerators. And I believe somebody mentioned a while back that NVIDIA actually has a paper where they're saying that in-memory compute can also be done for different ternary levels or higher levels in binary. I'm not very aware, but I think there is some work there. But the advantage of doing compute and memory with binary networks is because the memory footprint of the network is so small, you can actually store the whole thing on chip memory. So remember those memory A, memory B that we had? We can store the entire network there. So there is no expensive cost of moving the data between the main memory and so on and so forth. So binary networks there become very advantageous. Automated solutions like TVM and Glow are essential because exploration space is non-trivial. And as you get more and more complicated networks, it becomes really, really challenging, right? Also, compiler-based and particularly polyhedral-based optimizations might be very useful for things like ResNets, where you have different directed graphs, or even LSTMs for that matter. Last but not the least, so if you are doing tinyML and you're creating a product, you should have some understanding of how memory patterns are being done, right? If somebody sold me a chip, I would like to understand what kind of memory patterns can you support, right? For example, as you said, if you have a binary network and I bought an accelerator which does not support that kind of a memory pattern, it's going to be useless for me, right? So it makes sense to at least have some understanding of microcode. You should also understand the compute support and flexibility. If you have a 16-bit multiplier, can it do 4 4-bit multipliers? Can it do 2 8-bit multipliers? That will determine your flexibility in terms of compute, what you can fabricate. Does it support a black box toolchain support? So somebody has to do these optimizations. Either the vendor does it or you do it as a customer. It will be always beneficial because time to market will be much faster. As we saw, it is non-trivial to deploy an entire model in microcode onto an accelerator. While you do want some amount of black box toolchain support, you also want the flexibility of being able to tune the kernels, because there may be certain things that the compiler is doing, and you may want to get your hands dirty and figure out some scheme. Sometimes I've had a couple of cases where just padding a row of zeros has helped improve the kernel. But so that's about it, and only 4 minutes over to you. Any questions?
Great. Thank you. A couple of questions. One about for in-memory data locality. For in-memory data, locality in the same bank arrays are always a constraint. Is there any way compilers can help? I think this is kind of related to what you talked about data
Yeah.
locality. Okay. Uh, no, any comments you want to add on that, like compiler?
No, I think it's. I haven't, to be honest with you. I've looked at in-memory compute not for DNNs, so I don't think. But yeah, I mean, again, it depends upon the memory controller. And even if you're doing a memory bank on chip, it depends upon what kind of movement your clients can read and write clients can support with that. But yeah, definitely, if you are in-memory compute, it will be much easier, right, to access the data.
Got it. Got it. Yeah, and regarding the one-bit quantum thing that you mentioned, yeah, it seems like that's why many people have stopped at int 8 or 8-bit quantization and not really seen the benefits of going lower than that, not just maybe because the neural network may lose accuracy, but also I think when it comes to actual implementation, unless they do a radical hardware redesign to support,
Right.
you know, 3 bits or 2 bits or 1 bit or specific unique things like that, it's quite challenging to realize the improvement over int 8. So uh, that's a good point. Regarding the tinyML products, as no, just a comment, not really a question, is that many friends of the tinyML ecosystem, we do have many companies working on different parts of this. The toolchain support, tuning the kernels, and also hardware that support that they have like unique features, unique and innovative features that help with some of the challenges that you were talking about. That's not there in standard hardware. That's great. We actually covered almost all of the questions during the intermittent breaks that we had. So thank you for taking questions as and when they come up.
Absolutely.
Yeah. Cool. All right. Let me just request control back to going to the outro slides. Hey, thank you very much again, Manu. This has been very informative. I think for a lot of people who are new to tinyML and who work on a different sort of level in the tinyML ecosystem, understanding this kind of gets them across to the other side. So that's really great.
Thanks for the opportunity.
Okay. All right. I'm going to pull up a poll. Oops. Let me just show a poll, and panelists, please do, everybody, the attendees, please do answer the poll. This is very helpful for us um, to organize future talks. So I'll leave the voting up there as we continue through the slides. Okay.
I was about to vote myself, but then I realized it says you can't.
Yeah, a panelist can't vote. Only the attendees can vote. Sorry about that. Once again, we'd like to thank our sponsors. Oops, let me go back to the previous. Thank our sponsors: DeepLight, Kixo, Edge Impulse, Reality AI, Maxim Integrated, and SynSense. As I mentioned before, additional sponsorships are available. Please contact Betty at tinyml.org for more info. DeepLight. DeepLight uses AI to make other AI faster, smaller, and more power efficient. Visit bit.ly/deeplight for more info. Edge Impulse provides tinyML for all developers. You can go to get a free account for developers at edgeimpulse.com. Maxim Integrated, enabling edge intelligence through sensors and signal conditioning, low power Cortex M4 micros, and advanced AI acceleration coming soon. Kixo AutoML for embedded AI. Kixo provides an automated machine learning platform that builds tinyML solutions for edge using sensor data. Reality AI develops next generation AI tools for product development. SynSense builds ultra low power sensing and inference hardware for embedded mobile and edge devices. They design systems for real-time, always-on smart sensing for audio, vision, biosignals, and more. Once again, thank you to all our sponsors. And another reminder for our next tinyML talks happening on August 18th, 8 a.m. Pacific time. All right, thank you, everyone. Thank you for coming, and thank you, Manu. Let's continue the discussion on the forums. And as a reminder, the slides and video will be available in the next couple of days.